I won't talk much about deep learning, so that's perfect. Okay, so in my group, I actually not only working with documents, but also quite recently with in the fields of art analysis. So we have 2 projects there, with scene understanding in arts and also portrait similarity. And more related to the document analysis is actually our 3D document digitization project, which also get an extension of funding, which is really cool, because so here we try basically to scan documents in 3D. And so, for example, books or manuscripts which you cannot open anymore, to make them visible. And I advertise it here because I like to have real samples, which is quite difficult because, of course, there is some radiation with the CT image, and so no library so far has given us enough trust to send us some documents. So if you have maybe a document you're not really a fan of or something like that, then please get in touch with us. Okay, so let's go back to the topic of documents. And in letters, for example, in the bottom right one, it's quite easy to if you know the text, and you typically have the receiver and who sent the letter. So there it's quite easy. But if you have different texts, you can pose quite many questions like. What script type was it written? Which document category is it? Is it a notary charter or just a letter? How many writers wrote a document or a piece of a manuscript? So, and of course, what is written as well. And here we typically rely on of course, paleographies or experts in forensics or history. However, in the great age of mass digitization, this becomes quite time and cost intensive. So I just here have some numbers which are already outdated because these are from some months ago. So we have quite few manuscripts, and of course many more document images which are behind these manuscripts. And so we are in a need of automatic or at least semi-automatic methods. And from a computer perspective, we can put this in categories. So where is one or when is something written, and script type classification. This is all category of supervised or unsupervised document classification. Who wrote it or how many writers do we have? That would be writer identification, and what is written is then more handwritten text recognition. So at my lab, we now do everything, but so I will mainly concentrate here, of course, on writer identification. And so the remainder of the talk is basically, I will now give briefly an outline of the writer identification pipeline I use. And then at the second part, I will apply them on the GRK Papyri Dataset of Isabelle, and so that, just to see how it works or what can we do to improve the results here. So I spent the weekend doing that. And okay, let's first start with a brief introduction. So writer identification and writer retrieval. So basically, if you have a query sample and a database of known subjects and, of course, document images, then you can do writer identification. It basically means I classify hard the query image into one class, or what is more prominent or also more user-friendly, because then you not only see what the PC decided on is to make a writer retrieval so that you get the K most similar documents. And this is typically measured then not in accuracy, but in mean average precision. So you basically look at the total ranks and say what is the best rank in average. And this is a framework how it could look like, also just put together some weeks ago. So you can have a look at my laptop then later. So you could select here the number of nearest neighbors you want to look at, and select, okay, I just choose a specific ID here now of this data set. Of course, we have quite many challenges in writer identification. First of all, the within writer variability. If you write 9 times the word you here, it typically always looks differently. And of course, you can train yourself and to be as close as so that you 9 times it appears very similar, but you will have some variation. And the same also in the between writer variability, which we want to exploit in writer identification. Sure, if you have trained monks, this is both of these variations will be quite small, but there will be some variability. And you have also external factors. So the pen, of course, influences your writing style. So if you write with a ball pen or quill, it totally changes the writing style. And also, of course, also the material, so parchment versus paper. And external factors like artifacts, so like fold, stains, and so on, will, of course, make the results typically worse and more challenging for us. And methodology-wise, I quickly go through the pipeline now. So I follow mainly the approach which is also used in the fragments approach of Lamberg-Schumacher. It's a quite classic approach, I would say. So you sample so at some specific locations in the image. There you extract features. So nowadays they are typically learned by a neural network, and then they are aggregated, and then you compute some similarity measure. And because there was yesterday also quite a talk about pre-processing and sampling, let's have a look at that. So you have, typically I chose to use a binary image. So I binarize the image because then you get rid of the background and all these artifacts, hopefully. And then you can use, for example, keypoints, or you can restrict the keypoints to only lie on the foreground pixels. You can densely sample or sample densely at the contours. From if you have a binary image, that's quite easy to extract the contours as well. And for the local descriptors, we have already talked about SIFT descriptors, which I will also use later, but I don't have a visualization or something like here. Just a word to the learned features. So typically we have a neural network which is based on several layers, and then we often take the activation features from the last layer. If you have if you have a specific writer you want to look at, then of course you can also directly train for that writer. But the scenario we are typically dealing with is that we have a totally different test set. So training and test set, I have independent writers. And in this scenario, we need some features. And you can use, for example, the activation features of the last or the penultimate layer. If the last layer would be the classification layer, then it would be the penultimate layer. And use the CNN as a feature extraction. And then you can continue. So, and the last step or penultimate step in this pipeline would be then the encoding step. And here we basically, so if we have small patches, in this example, these are small patches, and I extract now with my favorite architecture some local descriptors, then I need somehow to combine them. So I want only one global feature vector. Because if I want to search in hundreds or millions of images, then it's good to have one small descriptor instead of a set of these local descriptors. It's just computational, much more efficient. And now I jump over the similarity. So a similarity, often you can just use Euclidean distance, cosine distance, or more fancy methods. Just to give you a feeling how good are the rates now in contemporary data. So this is a data set consisting of 250 writers in the test set. And the nice thing is that every writer had 2 samples written in Greek and 2 samples written in English. And so, of course, to also detect the other script is quite challenging. And so, nevertheless, we are here already at rates of over 99%. So, and even we can detect to some degree, so hard 2 or hard 3 means that the first 2 hits or the first 3 hits which I get are from the same writer. So if we have these clean images, it's only a small paragraph actually, but if we have these clean images, then the methods really work very well. Yeah. So and even we can detect to 77% here all 3 samples from the same writer ranked first. So yeah. In contrast, for historical, okay, before we go to historical data, just have a look at the few failure cases. So actually there were only 4 failure cases in this example from before, because 99.6% were correct. So 4 samples were not correct. Maybe one thing which you can directly see from the second example here, so the second row, is that it quite nicely gets the small, that it thinks that they are similar to each other, yeah, because on the small scale level, they look very similar. But of course, the left writer is not so, yeah, it's not a very clean hand here versus the right sample. So we see that the overall, if I would now also introduce patches from larger scale, probably also this example would have been detected correctly. Okay, so now in historical documents, there is a competition data set from 2017 consisting of about 720 writers for testing and each contributing 5 images. We tried that all these images come from different documents so that not only the background is something which gives a good clue. Yeah, so it's more on the foreground. And it's a letter collection, however, spanning quite many centuries. So it's not, of course, you have some form of granularity here. So it might be that due to the time variation, it's not so challenging, yeah, because we have spanning, I think, from 12th century to 19th century or something like that, and from this letter collection. So, but also here, we see that the recognition rates are about an order worse. Yeah, so we have here 10% more errors than before. So the best what we can get here is, I think, a little bit better. In my thesis, I got a little bit better, but around 90%. So in contrast to the clean benchmark data set, which we had before, where we are at 100, nearly 100%. And so I don't want to show off you more, just some, again, more failure cases actually, because these are the interesting things. So it seems that the binarization here, because I use the binarized images, I have a quite big influence on the recognition results. And also there are some samples which were obviously wrongly labeled. Not per se wrongly labeled, because we chose to be that the writer ID is the author ID. So of course there can be secretaries involved, and so the writer is actually not the same as the author of the text. And I guess this is the reason why some of the labels are obviously, from a writer perspective, wrong. Okay, so now let's come to the second part of the talk, using now writer identification on the Papyri data. And you may know that data set. So we have these 50 samples, so a quite small data set. I didn't use any deep learning based approach here. And so we have 4 to 7 samples per writer, written by 10 scribes. And there are 2 evaluation protocols, how you can evaluate that. either you take all the 50 samples and pick one out and test against all the others. This is also what we did for the other test sample sets. So in the contemporary data, all the recognition results you saw before were with this protocol, with the protocol 1. Or you choose the second protocol, where you classify, where you have 2 samples per writer, and you classify then using a classifier and train on them. And then you test on the remainder of the 30 samples. So, basic method with SIFT keypoints, SIFT descriptors on the original image, flood encoding. I have not talked here, and some more tricks. If you're interested, I can give you my configuration. It works to 30% roughly. So I'm a little bit below the baseline of Hussein et al., which is also created this dataset as far as I know. Okay, yeah, and so this is just was meant as a starter. Yeah, I thought, okay, yeah, well, it works quite difficult. Apparently, this dataset needs some more. And if we have a look at where the SIFT detector, so the key points where then features are extracted from, looks at, we see, okay, in this example, it works rather good. So the most key points are on the text. However, as already mentioned before, most of the case, they are also related on the background, so on the fiber. And if you have different documents, so which is natural with Papyri data, then this becomes quite difficult. So here are some more examples. Yeah, here key points are everywhere, not on this, well, occasionally on the script. And so now we have 2 possibilities. Yeah, either we make our system robust against the noise, and we can, for example, train our neural network with heavy data augmentation, and then it gets robust against that. Or we remove the noise and artifacts and so on, and this is due to binarization. And of course, modern binarization techniques actually rely on a neural network, which is trained with data augmentation. So 2 is often dependent on 1. But you could also use other techniques for removing the noise. Okay, so back to the Papyri dataset. I just used subinarization. It's a binarization technique by Su et al. 2010. And yeah, some work nice. Yeah, the middle one works okay. The other ones not so much. But at least we have some pictures which have less artifacts. And so the recognition results also quite drastically increased, from around 30% to 40%. And that was quite nice, and I was happy. That was at the end of last year, and so on the weekend, or last week, at the end of last week, I asked my colleague, which was actually working on binarization right now, hey, can you run it through your neural network? And sure, he said, and then we get much cleaner results. So now the right one is, yeah, I call it UNet++, because I didn't have a name for it yet, because it's based on a very popular medical image segmentation network, the UNet, and which is also, I think, from the BinNet we heard the day before yesterday. It's also probably the basis of that algorithm. And then the results get much better. Interestingly, if you have a look, let's here, yeah, in the middle, here it gets actually a little bit worse, but all the other samples are much cleaner, yeah. And also Angelos Nicolaou here, who did that binarization, he did a very good job here. And yeah, we can detect some more samples. So 6 more samples got correctly classified. No, 3 more samples, sorry, 6%. With 50 samples, of course, only 3 samples. But we see that there is an improvement. And then I thought, okay, why not also remove all the descriptors which are now in between lines? These actually can improve the recognition results. So if you leave them in modern handwriting, they improve the results because they give you a notion of how well people write on the line and how much is the spacing between the lines. So you have some information, but I thought maybe it's not so good for the Papyri data, so let's remove them. And so on the bottom one, we see that all the key points lying in between the lines are basically removed. And if we do that, we get even better results. So now one more sample, which was correctly, I mean, it's a small data set, yeah? But also in terms of mean average precision, we get higher results. Okay, and did I do more? I think not. But so we see that also if you look at the top 10 results, so the chance that the correct writer is under the top 10 is by 90%. So that's already quite good, I would say. But of course, in top 1 accuracy terms, we can do or improve a lot, I guess. This is the second protocol. Please excuse me, that was now before the results. These were leave one image out of all the 50 samples. And this is now I train on the 20 samples, 2 samples per writer. And I have a classifier now. I tested 2 classifier, just nearest neighbor or a linear SVM. And the combination with linear SVM and brought and the restricted SIFT key points are now at 60% accuracy, which is quite good. I mean, basically we doubled the accuracy rate, and from Mohammed Hussein. So that's quite nice. I think a nice first result, and maybe we can improve upon that. We can also have a look at the confusion matrix, but it's not really meaningful. We have one result which maybe sticks out a little bit, the one here. So Hermaus was apparently twice confused with the samples of Kyros. So apparently the writing style of both of them are quite similar. I don't know. It's just an idea. It could also be chance. There could be chance that that they are just looking very similar. Yeah? But the other ones, so the straight line here basically shows you on the diagonal that most of them are, so 60% are correctly classified here. Then before I conclude this talk, I would like to make some advertisement, because we also have, now we thought of using actually fragments. And my colleague Matthias Seré actually came on a nice idea how to create these fragments automatically. And so we will create for this challenge. Maybe Marie wants to participate. I would be really happy. So we will create about 100,000 fragments. So they are auto-generated, but then so we generate them automatically, and then we make sure that there is some text, because our focus here is on writing style, and not so much about finding actually joins. And this we thought to do for the next ICTAR, but this time also it's Latin text. So we also have squared bounding boxes, not only fragments like that. But I hope it gives you already an intuition, that this could also be used for creating papyri data from existing papyri data, fragments, and then run the same. The tool also will be made open source, and so you can generate your own fragments if you like to, and train your neural network. And I hope to find some participants here in the room. Maybe also you want to participate in fragment retrieval, because we cannot, of course, submit. So we need some submissions here for the ICFHR this year. So I will bring the homepage online in about a month, or no, less. And the fragments will be generated soon as well. Okay, so as a conclusion, I showed you the pipeline of writer identification retrieval. Pre-processing matters. Yeah, we saw that I chose the way of doing binarization, but we saw that this heavily improves the results. And which makes sense, because in contemporary data, our algorithms work really nicely because we can separate foreground and background so well with each other. And in contrast with historical data, we have many more problems. And in the future, I would like, of course, to get more robust against noise artifacts, and maybe also more fine-grained identification, so make it on a line-based level. Word-based is tough. I don't promise that, but line-based could work, to some degree. because also in the contemporary data, these paragraphs are actually quite small. So 2 lines or 3 lines are enough. So it could also work to some degree with 1 line. And yes, more on a further goal in the future, I would like to make a script analysis over the time, because we have now the mass data. It would be really nice to do this. We could, if there are labels, we could also integrate location. That would be quite nice to see how and when the script changes. Okay, thank you. So that was my last slide.